Plants use many types of pumps to move process liquids. One of the most common types of pumps in use today is a centrifugal pump. A centrifugal pump uses one or more impellers to create a centrifugal force that pushes the process liquid through the pump. While there are a number of different types of centrifugal pumps, they can be grouped into two basic categories: single-stage pumps and multi-stage pumps. Centrifugal pumps use centrifugal force to move liquids. Centrifugal force is the force that exists when an object or material moves in a circular motion. This force causes the object or material to move outward, away from the center of rotation. In a centrifugal pump, what moves outward is the process liquid. We can see how a centrifugal pump works by using this simplified illustration. All centrifugal pumps have an inlet, a casing, and an outlet. Inside the pump's casing is an impeller. It has a series of curved vanes that extend out from its center. The pump's casing is designed so that the area around the impeller creates a gradually widening spiral channel. This widening channel is known as the volute. Since this pump has only one impeller and one volute, it is referred to as a single-stage pump. During operation, a driver rotates the impeller, creating a centrifugal force that throws the process liquid outward into the volute. The outward movement of the liquid causes two things to happen. First, it creates a reduced pressure area at the suction eye of the impeller. This area of lower pressure draws more liquid into the pump and provides a constant flow of liquid. Second, it causes the liquid to gain speed. This happens because as the liquid is forced to the outside of the rotating impeller, it must move faster to keep up with the impeller. As the liquid flows away from the impeller, it spreads out to fill the volute. The expansion in the volute causes the liquid to slow down. The expansion in the volute causes the liquid to slow down and its pressure to increase. The increased pressure moves the liquid through the discharge of the pump and then on through the piping systems of the process. One way that centrifugal pumps can be categorized is by the way liquid flows through them. Three common flow path classifications are radial flow, axial flow, and mixed flow. In centrifugal pumps that have a radial flow design, the impeller causes the liquid to make a 90-degree turn and flow outward, or radially, from the suction eye to the tips of the vanes. A radial flow pump takes advantage of the maximum amount of centrifugal force that the impeller develops. Generally, radial flow pumps are capable of higher discharge pressures, but they don't move as much liquid as other types of centrifugal pumps. In centrifugal pumps that have an axial flow design, the impeller moves the liquid through the pump along a path that's parallel to the pump shaft. In this type of pump, the liquid is moved mainly by the propeller action of the impeller's vanes. This impeller uses only a small amount of centrifugal force to move the liquid. As a result, the discharge pressure of an axial flow pump tends to be lower than that of a radial flow pump. However, an axial flow pump may be able to move large quantities of liquid. Mixed flow pumps combine the characteristics of radial flow pumps and axial flow pumps. They use centrifugal force and the propeller action of the impeller's vanes to move the process liquid. For that reason, a mixed flow pump can develop a relatively high discharge pressure and still move a large quantity of liquid. In some installations, it's often necessary to keep a pump's driver above the liquid while the pump is submerged in the liquid. One type of centrifugal pump that you may find in these applications is a vertically mounted centrifugal pump. We'll use this illustration of a vertically mounted centrifugal pump and its driver to see how this type of pump works. The pump itself is submerged in a tank containing the liquid being pumped. The driver, which is an electric motor, is mounted above the pump on top of the tank. Its shaft is connected to the pump shaft by a coupling. This pump shaft is much longer than those found on most other centrifugal pumps. On any pump with a long shaft, it's important to keep the shaft in its correct position. so that the pump will operate properly. So several bearings are used to keep the shaft properly aligned. Now on this pump, there is no suction piping. Instead, the suction of the pump is submerged in the liquid being pumped. The suction is covered by a strainer, which prevents trash or debris from clogging the pump and causing excessive wear. The pump's impeller is also submerged in the liquid. This helps to ensure that the pump is always primed. This means that the casing is filled with the process liquid. During operation, liquid is drawn in through the suction and then pumped through the discharge piping, which extends up and out of the tank. All centrifugal pumps work by creating a centrifugal force. This force moves the liquid through the pump and increases the liquid's pressure. In applications where large increases in pressure are needed, multi-stage centrifugal pumps are often used. A multi-stage centrifugal pump contains 2 or more impellers and volutes in a single casing. Here's a simplified cross-section of a 3-stage centrifugal pump. Each stage of the pump has its own impeller and volute. In the volute, the liquid's pressure increases. Each of the first 2 volutes discharges into the suction eye of the stage that follows it. The 3rd stage volute discharges into the pump's outlet. So in this pump, the liquid flow path is from one end to the other. This is a 5-stage pump. It has 5 impellers and 5 volutes. The first 3 stages are located here, and the 4th and 5th stages are located here. But, as you can see, the liquid's flow path is different from that of the 3-stage pump we just saw. In this pump, liquid enters through the suction and flows into the impeller of the first stage. This impeller has a suction eye on both sides and is often called a double suction impeller. From the discharge of the first stage volute, the liquid flows into the second stage suction eye, then out of the second stage discharge and on to the third stage suction eye, and out of the third stage discharge to the suction eye of the fourth stage. The liquid from the fourth stage is routed to the suction eye of the fifth and final stage. After the liquid passes through the fifth stage, it leaves the pump through the discharge piping. Regardless of how the impellers on a centrifugal pump are arranged, or how many stages a pump has, the liquid's pressure increases as it passes through each stage. This creates a thrust across the impellers in each stage. This thrust, known as axial thrust, is caused by the difference in pressure between the suction eye and the volute. Because there is a difference in pressure across the impellers, axial thrust is created, and it tries to push the pump shaft toward the suction eyes. In order for the pump to operate properly, the thrust must be offset. On some pumps, the thrust is offset by using a thrust bearing or a device known as a balance piston or balance drum. On other pumps, the thrust is offset by the arrangement of the impellers. This pump has a balance piston. During operation, some of the fluid leaving the pump flows along the shaft and exerts pressure against the balance piston. That pressure tends to force the pump shaft away from the suction eyes and reduces the total thrust. Any fluid that passes by the balance piston is returned to the suction side of the first stage. Now on this pump, the arrangement of the impellers is used to offset axial thrust. Process liquid enters the first stage impeller from both sides, so the pressures on both sides of the impeller are equal. The suction eyes for the second stage and third stage impellers face in the opposite direction from the suction eyes of the fourth stage and fifth stage impellers. Since the forces caused by axial thrust are in opposite directions, they tend to cancel each other out. As a result, axial thrust in this pump is kept to a minimum. In this topic, we looked at the basic operation of several types of centrifugal pumps, including single-stage pumps, vertical pumps, and multi-stage pumps. Now let's try some practice questions that relate to this material. Inside all centrifugal pumps, an impeller creates centrifugal force to move liquid through the pump. Impellers can be designed in different ways, depending on factors such as the type of liquid being pumped and the amount of pressure increase that's needed. The impellers used in centrifugal pumps can be divided into three categories: closed, open, and semi-open. This impeller is a closed impeller. Its vanes are enclosed by shrouds on both sides. The shrouds direct the flow of liquid between the vanes. Closed impellers are often used with low viscosity or thin liquids. Liquids that are thick or contain suspended solids could clog a closed impeller. With those types of liquids, an open impeller could be used. This is an open impeller. As you can see, this impeller has no shrouds to direct the flow of liquid. While this design helps prevent clogging, it's less efficient at moving liquids than a closed impeller, since the flow of liquid is not directed between the vanes. Open impellers are used to pump thick liquids or liquids with solids such as slurries, and closed impellers are used to pump thin liquids. Semi-open impellers can be used for pumping thin liquids, since there is a shroud to direct the liquid between the vanes. They can also be used for heavier liquids and slurries, since they minimize clogging. Impellers can also be classified in other ways. For example, closed impellers can be further classified as single suction impellers or double suction impellers. This impeller is a single suction impeller. It has only one suction eye, so there's only one place that the liquid can enter the impeller. Single suction impellers are fine in applications where the pressure change across the pump is relatively low. In applications where the pressure change is higher, large amounts of axial thrust are created and must be offset. To minimize the effects of the axial thrust, some centrifugal pumps use a double suction impeller. A double suction impeller has two suction eyes, so liquid can enter the impeller from opposite directions. Because of this, the pressure on both sides of the impeller is the same, and axial thrust is minimized. No matter what type of impeller a centrifugal pump uses, the liquid being pumped gains pressure as it slows down to fill out the increasing volume of the volute. Radial thrust is a type of thrust that tends to move a pump shaft perpendicular to its axis. In a pump with a volute, the thrust is created by the difference in pressure across the volute. Now, some centrifugal pumps are equipped with a component that accomplishes the same speed-to-pressure conversion as a volute, but minimizes radial thrust. It's called a diffuser. A diffuser consists of a series of stationary vanes that surround the impeller. When we look at the vanes closely, we can see that the distance between the outer tips of the vanes is greater than the distance between the inner tips. As a result, the vanes create a series of small volutes all around the impeller. This arrangement of vanes balances the radial thrust around the impeller. Pumps require some type of seal between the pump shaft and the casing to keep process liquids in and contaminants out. Some pumps use packing to seal around the shaft. Other pumps use a device called a mechanical seal. On this cutaway of a typical mechanical seal, we can see the two basic parts: a stationary element that's attached to the pump casing and a rotating element that's attached to the pump shaft. Each element has its own seal ring. The two rings are positioned close together to form a seal that has virtually no leak-off. To prevent the seal rings from being damaged, some type of lubricant must be supplied to them. In some applications, the process liquid being pumped is used as the lubricant, but that's not always the case. When the liquid being pumped could be hazardous if the seal fails, or if it contains abrasives or other solids, such as in a slurry, an external liquid may be used to lubricate the seal rings. Many facilities use an independent system to provide lubricating liquid to the mechanical seals of several pumps. This is a simplified diagram of a typical sealing system. It provides lubricating liquid to the mechanical seals on all of the pumps in a process. The system consists of a storage tank, a filter, a supply pump and a backup supply pump, a low pressure switch, a pressure regulator for each mechanical seal, and a flow meter for each mechanical seal. For this process, an oil is used to lubricate the mechanical seals. During operation, the supply pump draws the oil from the storage tank through the filter. The filter removes contaminants from the oil to prevent damage to the sealing system pumps and the mechanical seals being supplied. The pump supplies the oil to the pressure regulators on each supply line. The pressure regulators control oil pressure and the amount of oil flow to each of the mechanical seals. The flow meters allow the flow to the seals to be monitored. If the supply pump fails to deliver the oil at the correct pressure, the pressure switch will sense this condition and automatically start the backup supply pump to restore pressure. At the mechanical seal, the oil lubricates the seal rings. The oil then passes by the seal, flows into the return header, and is sent back to the storage tank. From there, the oil can be reused.